In this video, I'm going to introduce magnetically coupled circuits. So first thing, what is magnetism? Magnetism is nothing but which can create attraction or repulsive force between a magnetic material. Okay, so magnetism is nothing but it can create attractive force or repulsive force between the magnetic objects. Basically, there are two ways to produce the magnetism. The first one is every current carrying conductor produces magnetic field. So whenever a current is passing through it, there is always magnetic field. Another one is permanent magnets always produces magnetic field. Okay, a permanent magnet, so there are two ways. The first one is every current carrying conductor produces magnetic field. A permanent magnet produces a magnetic field. There are two fields. One is electric field, another one is magnetic field. What is the difference between those two? Electric field always starts at positive and at negative, whereas magnetic field it always a closed path. So it is coming out of the north pole, okay, and then goes into the south pole, and there is a magnetic field inside that magnet too. Okay, so it's a closed loop. Same way when you look at a current carrying conductor, so here is a current carrying conductor. Say assume that current is going upwards, there is a magnetic field around this conductor, which is either rotating anti-clockwise or clockwise based on the current direction. So the current direction we can find out by using the right hand rule. Assume that hold a current carrying conductor in your right hand. If the thumb indicates the current direction, then the folding fingers indicates the magnetic field direction. Okay, say for example, this conductor is carrying a current. I mean, here it's open terminal, so definitely there won't be any current passing through it through open terminals. But assume that something is connected at this end. So assume that current is going upwards. So if my thumb indicates the current, I'm holding this in my right hand. Okay, if the thumb indicates the current direction, then the folding fingers indicates the magnetic field direction. So if the current is flowing upwards, there is magnetic field around this conductor going in anti-clockwise direction. Now, if I make this conductor as a loop, okay, if I make this conductor as a loop, assume that still the current is going in. Now the current is going in anti-clockwise direction. Current is going in anti-clockwise direction. So my thumb indicates the current direction, okay, and folding fingers indicates the magnetic field direction. So if I make this circle as for assume that there are four parts instead of a circle, assume that that's a rectangular square, okay, something like this. Okay. Now on this side, okay, thumb indicates the current direction, folding fingers indicates the magnetic field direction. That indicates that magnetic field is coming towards me. Because of the top conductor, magnetic field is coming towards me. Because of the left hand side, current is coming towards me, and magnetic field is coming towards me. Because of the down conductor, magnetic field is coming towards me. So wherever you see in this loop, magnetic field is coming towards me. Okay, so anywhere in this circle, the magnetic field is going to be constant. There is a formula, I will give you that. Now say for example, I'm going to make this as n number of loops. Okay, certain number of loops. Say here I made this as look like 4 loops. Okay, so if I have 4 loops, now because of the each loop wire there is a some magnetic field. Now the current is flowing in every loop in anti-clockwise direction, so there is lots of magnetic field in this loop. Now because of that magnetic field, this will this will gain a special character. Okay, that special character, because of that special character, we call this loop of wire or coil of wire is inductor. Okay, or the property of that inductor is nothing but inductance. So here is the property. So when there is lots of magnetic field inside of this, that magnetic field oppose the rate of change of current. Okay, so far we learned about magnetism. Now the magnetic field because of the straight wire is B equal to mu naught I over 2 pi r Tesla. Tesla is the unit. Mu naught is permeability constant. That value is 4 pi times 10 to the power of minus 7 Tesla meter per ampere. And I is the current passing through the conductor. R is the distance. So if I want to find the magnetic field at this point, then that magnetic field is mu naught I over 2 pi r. You can see as the distance increases, magnetic field strength is going to goes down. Now if I make that straight wire as a loop with a radius r, okay, with a radius r, okay, the magnetic field strength B equal to mu naught n I over 2r. This is the magnetic field at the center of that coil. B, magnetic field at the center of the coil. Now what I'm going to do, I'm going to make that number of loops, okay, into a coil with a length L, okay, with a length L. So I'm taking this length L, okay, and this is the radius r. Okay, now the magnetic field anywhere in this coil is going to be constant, and it's going to go in one direction based on the current flow in this coil. Okay, and anywhere that magnetic field strength is constant, that magnetic field strength B equal to mu naught n I over L, where L is the length of that inductor. We call this as inductor. Okay, n is number of turns, I is the current passing through this conductor, through the inductor. I is the current, n equal to number of turns. Okay, so I is the current, n equal to number of turns, L is length of the inductor, assuming that there is no gap between each turn. Okay, and n is number of turns. Mu naught is a constant. We just that's a permeability constant. That value is 4 pi times 10 to the power of minus 7. Now this coil, we call that as a solenoid, or also called inductor. Okay, now I'm going to define another term called self-inductance. Okay, inductor is a device, inductance is the property of the device. Okay, so inductance is the property of the device. Now self-inductance is nothing but because of a rate of change of magnetic flux in a coil and EMF induces in the same coil is nothing but a self-inductance. Okay, because of the rate of change of magnetic flux. So far I haven't defined what is magnetic flux. Magnetic flux we indicate with the phi m. Okay, phi m is the magnetic flux. Phi m is nothing but BA cos theta. Okay, where B is the magnetic flux, sorry, magnetic field. We just learned B value. Okay, and A is area of the loop. Okay, so here is a magnetic field. Okay, now if this magnetic field is passing through a square, so here is a magnetic field passing through the square. What is the area here? Length times width will give you area, times cos theta, where theta is angle between B and tangent to the area. Now tangent to the area is perpendicular to the area, right? So what is the angle between this tangent to the area and magnetic field? 0. So cos 0 is 1. So you will see the maximum magnetic flux. So magnetic flux is nothing but magnetic field passing through the area. Now because of the rate of change of magnetic flux in a coil and EMF induces across the same coil. So if you take a coil, okay, which is nothing but inductance, because of the rate of change of magnetic flux, when this B is going to change, we just found that in a conductor mu naught I over 2 pi r. Okay, r is the distance. Or if you look at the inductance, in inductance, that B value is we just defined B value is mu naught n I over L. Okay, this is for a single conductor, but if you look at the whole coil or solenoid, this value is mu naught n I over L. That's the B, magnetic field. Area is nothing but area of this loop. I know the diameter of this loop. Based on this I can find the area. Okay, so phi m is nothing but, okay, BA cos theta. Here theta equal to 0, so I can say phi m is nothing but BA. Now, because of the rate of change of magnetic flux in a coil, an EMF induces. So there will be an EMF induces. That EMF equal to N times d phi by dt, where N is number of turns. Okay, so induced EMF equal to N times d phi by dt. This is nothing but a Faraday's law. So self-inductance is nothing but, because of the current flowing in the same coil, and EMF induces in the same coil, that's nothing but the self-inductance. Now say for example, if this current is if this current is DC current, what is rate of change of current? 0. So is there any voltage across this? No, that value equal to 0. So that indicates that this inductor is going to behave like a short circuit in DC. When it comes to the AC, this current is going to change all the time. Whenever the current change, the B value is going to change all the time. So whenever there is rate of change of magnetic flux, or magnetic field, that indicates the magnetic flux. So whenever there is rate of change of magnetic flux, the EMF induces across this coil, that's called self-inductance. Now this E equal to, that's Faraday's law. Lenz's law is nothing but E equal to minus N times d phi by dt. This is Faraday's law, and this is Lenz's law. What is Lenz's law? What is the difference between Faraday's and Lenz's law? Both of them are same, but the Lenz's law indicates the direction of the induced EMF. This negative indicates that the induced EMF opposes the rate of change of current. So that's the reason here this is plus and that's minus. So if I put plus and minus, I don't need to put them negative there. So here it is. Okay, if I leave it E equal to, E is nothing but induced EMF, E equal to minus N times d phi by dt, assuming current is going in this direction, is same as Lenz's law. Is indicates that this is Lenz's law. The first one is Lenz's law. So Faraday's law just gave you the formula d phi by dt. Okay, these both are saying the same thing. Okay, that's about self-inductance. Now this E, I can write this as N times d phi by dt. What I'm going to do, N times d phi by di, and I'm going to say this is di by dt. Okay, now this N times d phi by di, we indicate that as inductance, L times di by dt, where L equal to inductance, that value is N times d phi by di, measured in Henry. Inductance is measured in Henry. Okay, I'll stop this video here. In the next video, I'll talk about mutual inductance. Thank you.